In the unforgiving physics of rotary wing flight, one equation has haunted engineers for decades. Lift must equal weight. But for heavy-lift helicopters operating from ship decks or austere desert bases, the real barrier isn't just weight. It's power density versus induced drag and ground effect, compounded by temperature and altitude. On paper, delivering thousands of combat-equipped Marines and their heavy equipment hundreds of miles inland, rapidly, from amphibious ships, should be borderline impossible. Hot desert air is less dense, reducing rotor efficiency. The power required to hover scales with the square root of the disk loading. Early heavy-lift attempts, like the piston-powered CH-37, hit hard limits. They could barely manage 8,000 pounds of payload before performance collapsed. Yet today, the CH-53 family, Super Stallion, and its successor, the King Stallion, does exactly that. Why? Because engineers refuse to accept the constraints of the atmosphere and the laws of thermodynamics. Visual. Maps of amphibious operations. USMC MEU Marine Expeditionary Unit. Concept art. Footage of Marines loading into CH-53s from LHD/LHA ships. External sling loads of howitzers or LAVs. Cut to geopolitical map highlighting Middle East logistics challenges. Vast distances. Limited runways. The U.S. Marine Corps' core mission is expeditionary. Project power from sea without relying on friendly airfields. In a high-threat environment, like potential operations near contested waterways, fixed-wing aircraft need long runways. Helicopters don't. The CH-53 provides a heavy and heavy lift, enabling a Marine Air-Ground Task Force to move not just troops, but a logistics backbone, artillery, armored vehicles, fuel bladders, and bulk supplies. A single CH-53 can excellently sling a 16-ton M198 howitzer or recover another downed helicopter. In recent large-scale exercises, waves of these aircraft have rapidly inserted battalions, turning a beachhead or forward operating base into a functioning combat node within hours. The military driver is clear. Speed of assembly in austere conditions beats massing forces slowly by sea or vulnerable land routes. Visual. Animated diagram of rotor disk. Induced velocity. Power required curve. Graph. Power versus altitude/temperature. Density altitude. CFD simulation of airflow over a 7-bladed rotor. Side-by-side comparison. 2-engine versus 3-engine configuration. Equation on screen. Power required is almost equal to weight caret 3 halves, /SQRT 2*ρ*A, where ρ equals air density, A equals rotor disk area. Why is heavy vertical lift so difficult? Start from first principles. In hover, a helicopter accelerates air downward to generate upward momentum. The power required is roughly proportional to the thrust weight, to the 3 halves power divided by the square root of air density and rotor area. Hot, high-altitude air, common in the Middle East, lowers ρ dramatically. A CH-53 at sea level might hover at max gross weight at 5,000 feet and 95 degrees Fahrenheit, high/hot Navy conditions. Lift capability can drop by 30 to 50% without more power. Early CH-53 models used 2 T64 turboshaft engines. The breakthrough for the E model, add a third engine. 3 General Electric T64. G416/419 turboshafts deliver around 13,000 plus shaft horsepower total. The main rotor grew to 7 blades from 6, with a 79-foot diameter, increasing disk area and reducing disk loading. The tail rotor is canted 20 degrees to provide some vertical lift component while countering torque. But power alone isn't enough. The transmission must handle massive torque without failure. Composite blades reduce weight while maintaining strength. Yet the fundamental limit remains. You're fighting gravity and the ideal gas law every second you're in a hover. Visual. Exploded view or cutaway of CH-53K, new GT408 engines, each 7, 500 shop, total 22, 500 shop, fly-by-wire controls, composite airframe elements. Animation of blade fold for shipboard storage. Sling load simulation. Comparison chart. CH-53E versus CH-53K payload/range in hot/high. The true hero moment came with the CH-53 CH-53K King Stallion. Engineers didn't just upscale the E-model. They redesigned from the ground up around new turboshaft engines, the GT408, delivering nearly 60% more power than the T-64 while being more fuel efficient and maintainable. Fly-by-wire flight controls replace mechanical linkages, allowing precise stability augmentation during sling load operations where center of gravity shifts can be catastrophic. Advanced composite in the airframe and blades cut empty weight while increasing fatigue resistance. The cargo cabin is 15% larger internally. Result: in high/hot conditions, the K can lift 27,000 pounds externally over 110 nautical miles, more than triple the E-model's capability under the same constraints. It can also carry 30,000 plus pounds internally or recover heavier aircraft. Digital systems integrate GPS, FLIR, and automated flight modes for all weather, day/night ops from pitching ship decks. This isn't marketing hype. It's the application of materials science, better alloys and composites for higher temperature tolerance in engines, and aerodynamics, optimized blade twist and airfoil to delay stall and reduce vibration. Visual: graph of specific fuel consumption, SFC, versus power output. Cost comparison chart: CH-53K unit cost, $90-140M, depending on lot versus F-35. Footage of maintenance crews on CH-53 showing high workload. Animation of exhaust reingestion issue historical and how it was solved. Reliability curves or readiness rates. But physics and economics demand trade-offs. More power means higher fuel burn. The CH-53 series is thirsty. Jet fuel logistics become a major constraint in extended operations. The E-model earned a reputation for maintenance intensity. The K was supposed to fix that with built-in diagnostics, but early testing revealed issues. Main gearbox durability, exhaust gas reingestion into engines, solved via redesign, structural fatigue in the tail boom, and software integration delays. Cost is the starkest compromise. A CH-53K flies at roughly $90 to $144 million per copy, often more than an F-35. Due to low production rates, developmental overruns, program costs exceeded $30 billion, and the complexity of ship-compatible folding rotors and heavy lift systems. Operating costs remain high. Readiness rates for the legacy E-fleet have historically suffered from part shortages. Popular misconception: bigger is always better. In reality, for many missions, the MV-22 Osprey offers faster cruise speed and longer range with less vulnerability on the ground, but far less raw lifting capacity. The CH-53 trades speed and agility for brute force. It's a specialist tool, not a universal one. Visual: forward-looking shots. CH-53K in flight over desert, Marines fast roping or vehicles offloading. Graph of life cycle cost versus capability gain. Closing montage of engineering simulations transitioning to real-world ops. Text overlay: human ingenuity versus the immutable laws of physics. Is the CH-53 family viable for the future? Yes, but with caveats. The King Stallion closes critical capability gaps for distributed maritime operations and contested logistics. It represents a genuine leap in what vertical lift can achieve under real-world physics constraints. Economically, however, it's expensive. Each aircraft and its support ecosystem demand significant investment. As production ramps and lessons from the E-model are fully incorporated, unit costs should decline, but heavy-lift helicopters will never be cheap. The alternative, relying solely on lighter assets or fixed-wing, risks operational failure in scenarios where runways are denied. In the end, the CH-53 story illustrates a timeless truth. Nature imposes hard limits: air density, power-to-weight ratios, material strength. Human ingenuity doesn't break those laws. It navigates them through clever compromises, iteration, and relentless first-principles thinking. Whether flooding a forward base with Marines or delivering precision logistics under fire, these machines remind us that real engineering isn't about shock and awe. It's about quietly solving the impossible, one trade-off at a time. Total word count supports 8 minutes at natural 150 to 160 WPM delivery, with pauses for visuals. Use high-quality stock/DoD footage, public domain where possible. Custom animations for physics/CFD. B-roll priority. Real CH-53 loading/unloading sequences to ground a flood in imagery without sensationalism. Sound design. Subtle rotor whoosh under physics explanations. Clean narration track. This script stays analytical, debunks hype where warranted, and centers the engineering story while tying back to the rapid deployment context.